Deep learning is a subfield of machine learning that focuses on models with many layers of computation. These models are capable of learning complex representations directly from data. This video explains what deep learning is, how it works, and why it differs from other machine learning approaches. Deep learning exists within machine learning, which itself exists within artificial intelligence. Understanding this hierarchy prevents confusion. Deep learning is not a replacement for AI or ML, but one specific approach among many. The term deep refers to the number of layers in a model. Deeper models contain multiple layers that transform data step by step. Each layer builds on the previous one, enabling more complex representations. Deep learning models are based on artificial neural networks. These networks are loosely inspired by biological neurons, but are entirely mathematical constructs designed for computation, not cognition. An artificial neuron combines inputs using weighted sums and applies an activation function. This produces an output that feeds into the next layer. Learning adjusts these weights to improve performance. Neural networks are organized into layers. The input layer receives raw data. Hidden layers perform transformations, and the output layer produces predictions or classifications. Shallow models contain few layers, while deep models contain many. Depth allows models to represent more complex relationships, but also increases computational and design complexity. One of deep learning's key advantages is representation learning. Instead of relying on manually engineered features, deep models learn representations automatically from raw data. Traditional machine learning often requires feature engineering. Deep learning reduces this need by learning features directly, which simplifies pipelines but increases data and compute requirements. Deep models learn hierarchically. Early layers capture simple patterns, while later layers capture more abstract concepts. This structure mirrors how complexity builds from simple components. Depth enables abstraction. Low-level signals are combined into higher-level representations that support complex tasks such as object recognition or language modeling. Deep learning requires large amounts of data. Without sufficient examples, deep models overfit and fail to generalize. Data availability is therefore a critical success factor. Compute resources are equally important. Training deep networks involves large numbers of matrix operations, making hardware acceleration essential. Graphics processing units enable deep learning's rise. GPUs perform parallel computation efficiently, dramatically reducing training time for large models. Backpropagation is the core learning algorithm used in deep networks. It propagates error signals backward through layers to update weights systematically. Deep learning supports end-to-end learning. Models map raw inputs directly to outputs with minimal manual intervention, simplifying system design. Deep learning excels in tasks involving unstructured data. Vision, speech, and language are domains where traditional methods struggled. In computer vision, deep learning enables image classification, object detection, and segmentation. Models learn visual features directly from pixel data. In speech recognition, deep learning models process audio signals to transcribe spoken language. Accuracy improvements made voice interfaces practical. In natural language processing, deep learning models handle sequences of text. They learn syntax, semantics, and context statistically rather than symbolically. Deep learning succeeded due to convergence of data, compute, and algorithms. None alone would have been sufficient. Benchmark breakthroughs, such as ImageNet, demonstrated deep learning's superiority in specific tasks. These results shifted research and industry priorities. Despite performance gains, deep learning sacrifices interpretability. Models often behave as black boxes, making explanations difficult. Opacity raises concerns in high-stakes domains. When decisions affect health, safety, or rights, lack of transparency becomes problematic. Training deep models is expensive. Time, energy, and hardware costs limit accessibility and raise sustainability questions. Large models are prone to overfitting when data is insufficient. Regularization techniques help control this risk. Techniques such as dropout and weight constraints improve generalization. These methods limit reliance on any single pathway. Deep learning is not general intelligence. Models remain task-specific and cannot reason broadly across domains. Deep learning systems do not understand meaning. They learn statistical associations, not concepts or intentions. Errors in deep learning can be confident and surprising. Small input changes may cause incorrect predictions. Models are sensitive to data shifts. Performance degrades when deployment conditions differ from training conditions. Deep learning is most appropriate for complex, high-dimensional problems involving unstructured data. It is unnecessary for simple problems. In many cases, classical methods are more efficient and interpretable. Cost considerations affect adoption. Training and serving large models requires significant resources. Deployment constraints include latency and hardware availability. These factors influence architecture choices. Maintenance remains ongoing. Models must be monitored and retrained as data evolves. Compared to classical machine learning, deep learning trades simplicity for scale and flexibility. Using deep learning everywhere leads to inefficiency. Choosing the right tool matters. Many systems combine deep learning with rules or simpler models to balance performance and control. Deep learning powers translation, recommendation systems, and perception tasks in modern products. Supporting infrastructure includes data pipelines, training platforms, and deployment tooling. Ethical implications include bias amplification and concentration of power among resource-rich organizations. Evaluation remains essential. Deep models must be tested rigorously using appropriate metrics. Governance frameworks help ensure responsible deployment of deep learning systems. Misconceptions persist. Deep learning outputs often appear intelligent, leading to overestimation of capabilities. Deep learning is an engineering discipline. Success depends on design choices, data, and constraints. Key strengths include automatic representation learning and scalability to complex tasks. Key limitations include data hunger, opacity, and high cost. The core takeaway is that deep learning is powerful but narrow. It solves specific problems extremely well. Next, we will visually compare artificial intelligence, machine learning, and deep learning to clarify their relationships and appropriate use cases.